So indeed, I'm Emma, and I want to talk a little bit about transport today, particularly some data that's been collected as part of a large observational study called PASTA, which is it's a big European FP7 project, but Imperial is heavily involved, and it's managed by a colleague of mine called Audrey de Nozel, who actually works in the Centre for Environmental Policy. So I'm going to talk a little bit about the data, which is quite an interesting data set, and I'll come on to the acronym in a minute. They seem to have lots of food-related acronyms for these various projects. So I think they obviously thought of the acronym first and tried to then work in all of the stuff around how they could make it make sense. So I want to talk about causal inference, and in particular the use of propensity scores and some of the dangers around that. I really want to highlight some of the issues that we keep seeing, I think, certainly recently in terms of statistical analysis of observational data. So I think it's going back to the ground, and I'm probably going to be preaching to the converted here just in terms of the issues of confounding. And of course, I'll talk a lot about counterfactuals and potential outcomes and so on. And then a look at some of the data. But firstly, how did I start, analysing transport data? Well, I actually started cycling into Imperial when my youngest son started at school, which meant that he was getting himself to school, and I no longer had to drive him to the Imperial nursery. And I'm very, risk averse. So my husband, who'd been cycling for several years, was like, you should start cycling. It's so much better for you. You'll feel less stressed, all this kind of stuff. So this was many years ago now, because my youngest son is now 19. But I did, being a statistician, I kind of decided I was going to find out how safe it actually was to cycle in London. And then I hooked up with a great friend and colleague, Dan Graham, who works in civil engineering. We have a transport studies group in civil engineering at Imperial, and he'd been collecting a lot of data around transport for a while. So we actually started collaborating and have now written several papers on transport statistics together, mainly using the Stats 19 data, which is all of the road traffic accident data. So it becomes rather morbid because I became interested in accidents. So then I collected all of the road traffic accidents, at least that were reported to police over a long period of time. And I used that really to dictate my route into work I live in Camden, and I obviously cycle to Imperial every day, which is in South Kensington. And now I've been cycling pretty happily for quite a while. A great point about cycling during COVID, when the lockdown first happened, I carried on with my commute, even though I was commuting back home. So I kind of set out from home and then cycle back. And I've been doing that every day ever since. But we're having to leave earlier and earlier to actually avoid the traffic, which is starting to build. So on the 6th of June, actually, this year, there was an American newspaper article claiming that 63% of Americans feel bike riding relieves stress and anxiety. And again, it's these kind of questions that I've been thinking about with the PASTA data actually pre-COVID, but it'll be interesting to see what the outcomes of all of the COVID-related cycling has been. Certainly cycling in London is getting very busy. So the question is that true? And what does it mean even to say that it relieves stress? Is that self-reported? How do we even measure stress? So first piece of data that I've been playing around with is the Strava data. I don't know if any of you use Strava. So I have a GPS tracker, and I obsessively monitor my cycling and my running. And I live kind of somewhere up here north in Camden. Hopefully you can see my pointer. And then I wheedle my way down through to South Kensington, and there's the Royal Albert Hall, and Imperial is here. So I do this every single day. This is a heat map from the 2015 data. This is a nice visualization. I didn't produce this one. You can see some of my terrible visualizations later. But what I do in the morning is I go and cycle around Regent's Park. And you can see this kind of heat map here as all of these people are cycling around Regent's Park. And I can't wait to see what the heat maps look like post-COVID, because the number of people that are cycling is just really increased in London. So I haven't got my accident map. I should have had that as well. But in fact, there are some real accident hotspots on my route that I managed to avoid, particularly here at the top of Hyde Park and so on. So I can look at the cycling deaths. I've done quite a lot of analysis of this kind of this data. One interesting thing about how accurate observational data is, of course, is that I don't run so much anymore, but I used to do a lot of running, and I had quite an old GPS sports watch, and it was a pain to switch between modes. It didn't do it automatically. So I always used to have it on running, including when I was recording my commute. So it had me kind of, running very, very fast through Regent's Park because I was on a bike. And then I don't know if any of you use Strava, but I actually got a message from a couple of people saying, oh, do you need any running training partners? And then I have to rather embarrassingly say, I'm not actually running fast. I'm just cycling incredibly slowly. My cycling's improved a bit during lockdown. So let's talk a little bit about PASTA. So the PASTA stands for Physical Activity Through Sustainable Transport Approaches. And it's a very big project. It's produced quite a lot of publications already associated with the data that was collected. But there are lots of observations. So there were a small number of participants, and they're tracked over a few weeks at different times of year. 40 in London, and Audrey is basically managing the project from London, but there are also participants in Antwerp and Barcelona, collecting 17 variables. So they filled in some quite extensive questionnaires, and then they also wear SenseWare, which measures all sorts of things, including they have their GPS tracking and so on, so you can see exactly where they are. And during the week where they fill in questionnaires, they actually outline in a very detailed way, along with the SenseWare, what they're actually doing, whether they're cycling and walking and so on. But then for the rest of the data, it's just them with the SenseWare, and we have to use some kind of mode detection algorithms, and I'll talk a little bit about that later on. But the SenseWare collects a huge amounts of data, skin temperature, GSR, which is the galvanic skin response, which I'm going to talk about later on, speed and so on. So we've done some work in terms of doing mode detection from the GPS and the speed for the data that doesn't have the actual type of transport, but you can imagine there are all sorts of issues associated with that. So we've got lots of nice information about the people that participated in the study. And you can have a look at here just in terms of how that data is correlated. And as you might expect, there are heat flux and near body temperature have these. So you've got negative and positive correlations, and they're the ones that you might expect. There's an income and city association, quite a small one, but you've got it's quite a complex data set with some quite high correlations when it comes to some of the analysis that we're going to look at later on. But now I want to take a step back from the data, which I'll have a look at in a bit more detail later on. But how can we actually harness this data to quantify causal effects that we might be interested in? And the things that they've looked at already is, does promoting cycling reduce obesity? Does cycling reduce stress is the one that we're currently looking at. What mode of transport has the most health benefits, and so on. So there's quite a lot of work being done. But Audrey initially came to us. So Audrey is not a statistician. She initially came to the stats section because she was getting some very strange results around GSR, which is the data that's supposed to measure stress, in that it was giving her, if you just do a very naive look at the data, it looks as if your GSR is much higher when you're cycling compared to other activities. So there's loads of publications on why GSR might be a good proxy for stress. But of course, it's also, if you're sweating and you're exercising, your GSR also tends to increase. So you need to be very, very careful in the analysis. And if you do a bog standard before and after type analysis, it doesn't give you the kind of correct answer because of the joys of kind of confounding. So of course, confounding, I'm sure you're all well aware. I mean, we all know everything about correlation and causation. And one of the major issues, amongst many others, when you're trying to do the impossible feat of any causal inference is one of the issues is confounding. So that's basically when a measured treatment effect is explained by some other unmeasured factor. And clearly, it's an important cause of spurious correlations in data. So the example I kind of like to use when I first introduce this when I'm teaching is, apart from the cigarette lighter in your pocket giving you cancer, obviously is that, things like having bigger feet makes you a better reader. And I normally catch a few people out with this, but of course, this is where giving a talk virtually or remotely has its disadvantages, because I can't get any kind of audience interaction. But of course, the confounding variable here is age, in that you tend to not be so good at reading when you're a newborn. So the question is, does cycling make you less stressed? Here's another. What potential confounders? Unfortunately, I can't see the chat for the meeting. Otherwise, I might be able to see some answers in the chat. But I'm presenting, so I can't. But does cycling make you less stressed? What potential confounders could you have there? Well, it could be lots of things. I mean, it could be the fact that generally healthier people are the ones that cycle, and they're the ones that are less stressed. So you have to be quite careful, of course, with any of these analyses, but nonetheless, that doesn't mean that we should ignore all observational data and not try to draw conclusions. So I only got into causal inference relatively recently, when I started working with Dan Graham, so 10-15 years ago or so. And that's relatively recently for me. I started off really as a kind of a time series analysis and wavelets kind of person. But I've become more and more interested in causal inference, I guess, because of the challenges it promotes. But when it comes to accident data, one of the first things I do now is just do the standard DAG. So I start to look at the graph, thinking about what possible variables might impact what I'm interested in. Another set of data that we have looks at whether speed cameras actually reduce accident rates. But of course, one of the issues is that you have loads of confounding here, because in fact, speed cameras are only generally introduced into areas where you've had problems with accidents and traffic volume and so on in the past. So you have to have a certain number of accidents before they'll put in the speed camera. So there are all sorts of issues with making any causal inferences there. But we have to try and take account of this. And of course, traditionally, we've just used outcome regression. And whenever I talk to David Cox, who's been mentioned already in the previous talk, he tends to say, "Oh, do an outcome regression." And we've discussed this this propensity score approach on many occasions, and he's definitely not convinced, and neither am I, but I can see some advantages, so I'm happy to I'll outline that in a bit more detail. But I do love the beauty of the potential outcomes framework, and it's the thing that I use generally when I'm teaching. Interestingly, maybe many of you will have had different experiences, but as an undergraduate and even as a master's student studying, well, as an undergraduate, mainly mathematics, but as a master's student, mainly with the statistics I was studying, it never really approached that kind of causal inference question. For those that have more maybe kind of biomedical-y type courses, you tend to think about it more carefully, but generally the setup was about having nice randomized controlled trials, and it's just talking about models of association, and the thorny issue of causality never really came into it. But of course, I really like this idea of having these potential outcomes, and how you think about your outcome under control and treatment. And of course, if we didn't have this issue of having these, if we could obviously, if I could measure both my potential outcomes, so the outcome under treatment and the outcome under control, then we wouldn't have this issue of causal inference. It would just be a matter of really arithmetic, working out your treatment effects. So the issue being that, of course, we're only measuring one outcome. So my morning headache when I take my paracetamol, I can't rewind and not take the paracetamol and see the outcome. I'm only measuring one of them. So what we're interested in is how we account for that when you're going to have all of these issues with what are effectively the joys of conditional probabilities. So my unobserved outcome is known as my kind of counterfactual. And in this kind of cycling stress situation, it would be, would I still be stressed the same level of stress if I wasn't cycling? And I can't measure that because I cycle. So I'm interested in my population level effects generally. So I might be interested in the average potential outcomes, so the expected values of y0, which is the outcome under control, or the expected value of y1, the expected value under treatment. And my average treatment effect is just the expected value of the difference of those two. I could, of course, sometimes I might be interested in my ATT, so the average treatment effect of the treated, but I'm going to be concentrating mainly on just average treatment effects at the population level. Now, if I could do a randomized control trial, that would be fantastic. I could probably do one just on myself, but we all know that there's huge amounts of observational data now, and we just don't have the capacity to do RCTs. I've been in this educational setting that we find ourselves in now. I'm really interested to see the differences between outcomes for remote versus on-campus teaching. And again, I'm not going to have my counterfactual. And I wish that I could randomize. I'll have, so what we will have in October, I don't know how you guys are coping with everything, but we are allowing students to start remotely, but we will be having some on-campus teaching. And those students that are starting remotely will give us a group of students that are doing it all remotely, but of course, they're not necessarily a randomized group. I can't just say to my students, right, 100 of you go remotely and the rest of you to come on campus, and I'm going to allocate the treatments. But it will nonetheless be interesting to do some proper statistical analysis of the differences. And normally at this point, I'd ask if anyone recognises, and I see that I'm at a stats conference, so one would hope that many of you recognise the Fisher. I'm not going to get into the history of Fisher. I only have second information about him. But what I can say is that there he is smoking his pipe, and we all know the work that he did in terms of not having an association, a causal link between smoking and cancer. So it's one of the common things that we use when we're talking about causal inference. I particularly like this photo because he's there smoking his pipe. So of course, as I've already said, the statistical tools are designed to study association, not causation. Should we be skeptical of causal inference methods? Well, of course we should, and I should say that really from the outset, even though I'm trying to do causal inference myself. So issues with observational studies, treatment selection is influenced by subject characteristics. So your baseline characteristics of the treated group can obviously differ systematically. And historically, and as David Cox keeps telling me, I should just be using outcome regression models, so some kind of regression covariate adjustment to control for that. But nonetheless, and I do still think outcome regression is great, there are still some things that it doesn't take into account for, things like overlap that I'll come on to later on. So I am going to introduce propensity scores, and I'm sure many of you are already aware of these. So I'm going to discuss propensity scores because they're just a nice way really of getting some kind of balance amongst your covariates, and they're a great way of kind of reducing dimensionality as well of reducing dimensionality of your data. But of course, we know that comes with lots of issues as well. So for randomized control trial, obviously treatments are assigned randomly in whatever mechanism that you're going to use, and then we can get our unbiased estimates, because our treated untreated groups are exchangeable, by which I mean the Y0 and the Y1 here are conditionally independent of D, the treatment. So in that case, my conditional expectation of Y given treatment status is just the expected value of Y, and we have no issues. So the ATE and the ATT in this case just coincide. Observational studies, no randomization. This is a disaster potentially, and of course, in general, that the conditional expectation is not the same as this unconditional expectation, and you can have some really large biases, which is pretty much what Audrey was observing when she was just doing her before and after type approach to GSR measurements for cycling and non-cycling groups. So propensity scores. I mean, I think that it's really beautiful mathematically. So I think that if you read the original papers, it's a very nice piece of work. The propensity score is just a probability of treatment assignment, conditional on some baseline characteristics, and it allows us to, in some ways, mimic our observational study with a randomized control trial. So it's a balancing score, conditional on your propensity score. The distribution of those characteristics is going to be similar between treated and non-treated subjects. So you effectively have what looks like a randomized control trial that you can then have at least some credibility in terms of those treatment effects actually measuring the true treatment effects. So the 1983 paper that everybody quotes is the Rosenbaum and Rubin one, and they just have pi being the probability of being treated given your baseline covariates, xi in this case. So DI being one. Here I'm just talking about the case where you're treated or not treated. There's been a lot of work looking at continuous treatments as well. And then conditional on that propensity score, your covariates match. So you can create a nice kind of matched group of treated and controls where they come from, if you like, those populations that are similar in some sense. Now, of course, we know what a propensity score is in a randomized control trial because we've designed the study. So we've allocated our treatments and we know that exactly. We have to estimate it in observational studies. So once we've estimated the propensity score, then we can make use of it to analyze our treatment effects or estimate our treatment effects. There are big issues even around estimating the propensity score that I'll come on to later. Well, I'll come on to now. So you have to have some very, very strong assumptions on the propensity score for it to really be useful. So one of which is this strong ignorability, which means that conditional on your covariates, the xi's, you have the condition that we were discussing earlier on in terms of your y0 and y1 being conditionally dependent of given the DI. You also need to have your propensity score not being 0 or 1. That's pretty critical. So you've got this is strong ignorability, and if we have both of those conditions holding, then we can obtain unbiased estimates of the treatment effects. And it's a really beautiful paper, I think, the Rosenbaum and Rubin work of '83, and subsequent papers by both authors. The issue, of course, is that strong ignorability is a very, very strong assumption. Effectively, what we're saying there is that the treatment assignment is independent of the potential outcomes as long as we know our baseline covariates. That is equivalent to saying we have no unmeasured confounders. And how often is that reasonable? Who knows? You might. So there's lots of questions about, shouldn't we just do a standard outcome regression then if we know, if we've measured if we have, otherwise you might as well just do a standard regression where you take account of your covariates. Of course, the second one here is that every subject has a non-zero probability of receiving the treatment. Otherwise, you can't really estimate anything. So there are quite a few ways of thinking about how you might use propensity score. The first is just matching. So we match subjects with similar propensities, and then you can estimate your treatment effects from those two groups. Often you'll do pair matching. There are lots of ways to do it. I'm looking at the time and I'm realizing I'm going to have to speed up a little bit. But of course, in the randomized control trial, we have to also note the fact that there exist differences between covariates for the treated and control groups, and it's similar for propensity score matching. You can also do different things like stratification and so on. I'm going to think more about using my propensity scores to weight my treatment. So this is inverse probability of treatment weighting, and what you do is you weight your propensity score, if you like, in some respects, to obtain a new sample that takes that into account, and then you can very simply get an unbiased, well, supposedly unbiased estimates under the strong assumptions of the treatment effect. So let's go back very quickly in the last 5 minutes to this PASTA data before I talk about the results in terms of stress levels and cycling. So these are now my terrible graphics, and this is going to be terribly ungracious of me, but these were produced by my wonderful PhD student Helen. So I'm not blaming her for the quality of the graphics. It's more the fact that I was rushing around last night trying to get a hold of them. So actually, this is the data as collected over the over 3 million observations we can have, and you can see that the majority of the time people are sleeping, or those of us that have been in lockdown sitting in front of Teams meetings all day, we spend a lot of time stationary. But I wanted to include this plot just to kind of look at the distribution of what people are doing. Most of the time we're sitting or sleeping. And then we can see cycling and others amongst them, but digging a bit deeper, taking out that where we're stationary data. And again, I haven't included, so it goes cycling, walking, and kind of motoring, car or van or whatever. So the first bar here is cycling. So you're cycling, walking, and then motoring, and then the kind of pink one is just other modes of transport, pedalo or something, whatever. Or we haven't measured it, which is the majority of the cases. We know they're moving, but we don't know the mode. We haven't been able to identify it. So, You can see it's going to be really interesting post-COVID. I want to redo the data post-COVID to see actually what's happened in terms of people's commuting behaviour or travelling behaviour. But you can see that you're more cycling in Antwerp than London and Barcelona. Barcelona is really low on the kind of cycling. Remember, we've got cycling first, then walking, then motoring. And then you can also look at the split by gender. So I cycle in London, and it's certainly the case that there are far fewer women cycling than there are men. And that actually seems to be, from what I've seen during my cycles during COVID, that's still true. Far more men on bikes, you know, and whether that's a safety aversion risk issue, who knows. Most people, this is a self-reported health status in terms of whether people felt they were in excellent health or, you know, very good, fair or poor. Most people feel that they're in good health, but especially those that cycle and walk. So a couple of maps of just a couple of examples of individual data and individual analyses. And again, this is kind of from Helen, so my PhD student. Thank you for producing these. But you can kind of look at the speed of how people are cycling. So these are cyclists, and you can see that this is basically the kind of more orangey, in the spectrum, the faster you're going, and down at blue is cycling very slowly. It's really gridlocked around here in South Kensington. Similarly around here on shopping streets, on Marylebone High Street and so on. You see people are picking up speed as they storm along the Euston Road, for those of you that know London. And similarly through Hyde Park. This is part of my commute every single day through Hyde Park. It's wonderful. I actually have a really excellent, safe, relatively quiet route now that I have all the accident data. So what we did was we did some quite extensive analysis, creating treatment groups. So looking at whether people were cycling versus other modes of transport. Now we're using this GSR as a proxy for stress. There are lots of issues associated with that, but there have been various studies that show that it is a good measure of stress. But of course, it causes all sorts of issues because you tend to get a rise in GSR when you're exercising as well. So we decided that a sensible look in terms of trying to get at least some covariate matching would be sensible. Because then we could take account of that, because it would take account when people are exercising, when they're self-reported as exercising and so on. So we did the standard logistic regression with covariates to get at our propensity score, i.e. the probability of treatment, using those variables that were significant. And then we compared the naive approach, which I just realized as I looked at the slides before I haven't reported, to outcome regression, and then this inverse weighting approach, and also an augmented regression, which is where you actually include the propensity score in a more complicated model, statistical model. So finally to the results, and also apologies because I have the confidence intervals but not on this slide, but they are all significant. So if you look at even the outcome regression model is showing a kind of close to 8% reduction in GSR for walking, 17% for cycling, and then it's an increase for motoring, demonstrating, at least from our analysis, that there's some increase in stress when you're driving compared to other modes of transport. And then we're getting similar directions on our propensity score approaches, but the augmented regression giving kind of larger values compared to the others. And then the conclusion, I guess, this is all literally this analysis is one that we've only just been completing, but our preliminary conclusion is that certainly you're looking as if you're less stressed when you're cycling and walking, and more stressed when driving. But of course, there's a lot more work to do, because we need to really think about times of day of travel, and that data is really quite complicated and is a big part of my PhD students' subjects by her thesis. One thing to say is that Audrey was very happy to see these results, because I think that other analysis had showed that cycling really does reduce stress, certainly in self-reported stress, so that it's good to see that some of the GSR analyses are backing that up. So a couple of things in terms of the limitations really of PS score before I finish. Basically, it's this dimension reducing score. So I think if you can do an outcome regression and you know that you've measured your confounders and you've got good overlap, which means that between your treated and control group, you've got good overlap between your covariates. I do still think an outcome regression is the way to go. One of the nice things about propensity scores is that you can then do if you have nonlinear relationships and so on, because you've just got one measurement, it's actually quite good in some of the more complicated kind of modeling. But it does adjust pretty effectively for measured confounding and finds this common support. So my final comment really in terms of whether we should be doing before and after type study is for those of you that looked at the kind of Royal Statistical Society kind of when they used to have wonderful discussion papers. Ehrenberg wrote this amazing criticism of a great paper by Harvey and Durbin, saying that the authors should have just reported all their time series mumbo jumbo made no difference, because in that case they had a before and after good result for wearing seatbelts in terms of accidents. And Harvey and Durbin had this brilliant response, which I think really kind of says, their tirade contains little in the way of relevant rational argument. So do go and look this up. It's obviously published in the RSS. And I do love going back historically through discussion papers when they used to be maybe more brutal than they have been in recent years. We tend to be a bit kinder to each other these days. I guess my final view is that I do think coherent use statistical methods has an important role to play in this kind of data science field where the majority of the data is observational, and we have to be incredibly careful, even more so. We've all seen this recently with people producing analyses that from observational studies without really thinking about whether you can make causal conclusions. So I'm going to stop there and stop sharing my screen.